you are all keeping well. Thank you for making the time and attend this technical talk. I am Ali Reza. I'm the joint PES chapter chair, and I have with me Dean, Region 10 PES representative. So the title for today's talk is Impact and Management of Harmonic Distortion for Large Renewable Generators, presented by Jason David from the University of Wollongong. Jason is a research fellow at the University of Wollongong with the Australian Power Quality and Reliability Centre. Jason continues his contributions to the field undertaking industry-supported research and commercial research projects, investigating the practical management of harmonics and harmonic modeling in power systems with high penetration of inverter-based resources. Jason is currently convening a SIGRAE international working group titled Specification, Validation, and Application of Harmonic Models of Inverter-Based Resources, and is the secretary of the Australian C4 panel. Thank you for accepting our invitation, Jason. The floor is yours. Please start. Thank you.
Thank you very much for the kind introduction, Ali, and thank you everyone for tuning in and taking a bit of time to have a look at this presentation. So, as Ali mentioned, I am a research fellow with the University of Wollongong. In the past, I'd say probably about 4 or 5 years, I've been focusing solely on harmonics, harmonic modeling, harmonic management, assessment of compliance, mitigation, all sorts of things, really anything to do with harmonics, and I've been doing it. We have seen a significant rise in interest in this area in the past probably 4 or 5 years, mostly around how the impacts are changing and how the targets are moving with the increased penetration of renewable energy generation. And so this project, this presentation, is a very brief overview of a project that has recently wrapped at the University of Wollongong. It was funded by ARENA, the Australian Renewable Energy Agency, with a consortium of industry partners. But really, this project was built, written, and undertaken based on the experiences that we've been having here at the University of Wollongong. So I was just mentioning to Ali that we do quite a lot of straight out consulting at the University of Wollongong, and just about anything that comes in to do with compliance assessment, harmonic modeling, anything in that field is generally what I'll be undertaking. And in that experience and in that time, we've really identified some key areas where we think that there are some real issues with the business as usual sort of thing. And so this project goes, I think, in my opinion, part of the way to addressing some of those issues. But there's still quite a long way to go before we really hit, I suppose, a more efficient and a more appropriate and a more fit for purpose process when it comes to harmonic management, particularly in networks with a huge amount of renewable energy either connected or expected to connect. And so this project kind of is, I suppose, the incubator or the introduction to a lot of the concepts. And as you can see in section 6 there, that we've also identified quite a number of very important future activities that we think certainly is required to further this work a little bit further. So just very briefly, what we'll be talking about today. So it'll be a brief project overview, just kind of some of the details and the motivation behind it, although kind of been giving you a bit of a preview to that already. And then some of the key research activities that were actually undertaken, starting with an actual review of distortion levels across the globe where we were able to get data. We then looked at different harmonic allocation methodologies, how we actually manage harmonic distortion in power systems, and identify where the real weaknesses are when we start talking about renewable generation. We then look at harmonic source aggregation. So anyone who has done a little bit of modeling or done a little bit of analyzing of harmonic data or harmonic models might be somewhat aware of either the phrase harmonic source aggregation or alpha law or summation law, or I think there's a few other names for it as well, but that's kind of looking at how two different harmonic sources actually interact with each other. We then look at some of the impacts of compliance assessment, and as I mentioned before, some future activities, and there's also be plenty of time for a bit of a discussion at the end. Actually missing in that list there as well is actually a good bit of work that we did looking into mitigation, which is also in the presentation, just isn't there in the contents. So as I mentioned, this project ran for about 18 months and wrapped, I think, mid this year, June-ish this year. It was predominantly funded by ARENA, but we also got quite a significant buy-in, as you can see, from industry partners as well, across a range of stakeholders, which I always find quite interesting as well. So we've got our NSPs in there, but we've also got developers in Brez and Neoen, and also an OEM and investors as well. So this topic, this issue of harmonic management and compliance assessment and modeling, it's present, it's there, we understand it, and it's becoming quite understandable throughout the industry now that something needs to be done, and we certainly saw that in this project, which is a really good outcome. So very briefly, when we talk about harmonic distortion, there are some things that it is, some things that it is not, or at least in this context, some things that it is not. One thing that it is not that we're talking about here is transient interactions. We're not talking about short-term effects. We are talking about long-term steady state harmonic distortion. And the reason we're talking about that is because, well, one, it needs to be managed by law. It needs to be managed by NSPs. It is referenced in the NER. There are Australian standards that are published on it. There are also plenty of application guidelines and all sorts of things. So we're talking about long-term steady state harmonic distortion, and really the context or the reason why these are the focus. I'm just going to pull up a laser pointer. The reason why is because it starts to have these sorts of long-term effects, particularly with losses and increased degradation of insulation. In some cases, we can actually see catastrophic failure due to harmonic resonances, particularly with harmonic resonances. You might see a capacitor bank that is switched in, it resonates with the network, it sinks a significant amount of harmonic current and goes bang. And interaction with power electronic controllers. Now that is kind of edging onto the transient impacts. Might have heard the phrase harmonic instability, but it is still very, very real, and it is still something that certainly needs to be managed appropriately. But I suppose it's something that is becoming more and more visible, I suppose, because of the discussions that are now being had. And so ultimately, network service providers need to manage that harmonic distortion on the network. And so this, I suppose, in a very roundabout way, what I'm trying to get at here is that the processes we have identified to manage harmonic distortion are ill-designed, leading to dispute. They are ambiguous. They may not be optimal. They may not be leading to optimal outcomes. And so we're starting to try to tease apart some of the big issues that we're really trying to find, which we'll talk about in a bit. So some of the key research activities, before we get into the nitty-gritty, some of the key research activities. First, we really looked at power system distortion levels. So looking at, as I mentioned, where we had data, we looked at trends, long-term trends of harmonic distortion globally. To really look to see what distortion levels are doing, because we're now experiencing this significant increase in connection of renewable energy generation all over the world. We know that. And so getting a hold of trends of distortion provides a very interesting insight as to exactly what's happening, because it might be fair enough to assume that, well, we're connecting a lot of harmonic sources, so our harmonic distortion is going to go up, but it's not always that simple. To put it that easily, it's not always that simple. So it's always worth a review to kind of see where we're really sitting. We then have a critical review of the international of harmonic emission allocation procedures that are being used worldwide. Some of you may be familiar with it, but certainly we'll be focusing on the Australian standard that references it. I mentioned briefly the summation law and the aggregation of harmonic sources. So this was a very, very important and very interesting work package of the project. As I mentioned, review of mitigation strategies and how we actually mitigate when we find there's an actual issue. How do we actually mitigate harmonic distortion? Again, findings were really quite interesting. And a preliminary look into how we're assessing compliance. As I mentioned, there is a lot of ambiguity around, and certainly something that needs a lot more definition. I don't know why that's being highlighted. So just also this presentation is kind of a Frankenstein of a lot of presentations. You'll see there's a number of publications that came out of the project. They're all, I think they're all almost publicly available. If not, they will be soon. If anyone is interested in more information, if anyone wants access to publications, please just get in touch. Please feel free to contact Ali, and Ali, I give you my consent to pass around my contact details. If someone wants to talk harmonics, I'll always pick up the phone. So please feel free to get in touch. And Ali and I were talking previously, Arena's goal is to share knowledge, to make things accessible. So when findings are made within an Arena project, they need to be published and they need to be shared. That's part of what we're doing here today. But what ultimately I'm trying to say is that these slides, as a tax-paying citizen, these slides belong to you. So feel free to get in touch. If you want the slides, you can have them. If you want more information, if you want to discuss, please, yeah, always keen to talk. All right, so just to get into some of the more technical component of this presentation. So as I mentioned, our first step was really to kind of get a handle on what is distortion doing at the moment, because now that we're a good, couple of years, well, more than half a decade to a decade into connecting a significant amount of renewable energy generation. And so if something needs to be sorted, then surely we'll be able to see that in trends of distortion as these things connect. So we found two databases. When I say find, one of them actually belongs to the University of Wollongong. It is the long-term power quality compliance audit that is being run by the University of Wollongong, and specifically the Australian Power Quality and Reliability Centre, of which I'm a research fellow. And ultimately, it is a collection of power quality data that has been collected from over its years. It's been running for about 20 years now. It has had at one time or another every single NSP as a member of the PQCA. So we now have quite a good visibility of distortion over a long period of time, like say about 20 years. It's certainly not a continuous database. There are certain sections where there are gaps. There are some where, it's only a short amount of data, but it gives us a good idea and it gives us the ability to actually look in some level of detail exactly what's happening as renewable generators connect. And the second database that was polled was actually hosted in the Netherlands. And again, that database is openly accessible. This was not through contacts. This was not through, a research agreement or anything. This is simply by Googling or search engine equivalent, and came across the power quality database that a Netherlands consortium titled Netbeheer Nederland actually hosts. And if you're interested, it's quite interesting. And what that ultimately gave us was the ability to look at years and years and years worth of data that was hosted by the NSPs themselves. Netherlands, you might be aware, has and is continuing to connect a substantial amount of offshore wind farms. And so ultimately what we did was found a whole bunch of substations for which there was enough data prior to the connection of the generator and post connection of the generator. And we found, I think there was actually 4 wind farms that were ultimately analysed, 3 with very, very strong trends that were defined. And I've presented 2 here. But again, if you want to know more information, there is actually one thing I haven't mentioned is there is about a 120-page report that is available on our website. Again, if you're interested, go to our website or get in touch and I'm happy to share it. So everything that I'm presenting here actually is providing much more rigor and detail in the report as well. So it's really just a high-level snapshot. So the first site that we had a look at was in Australia. It was a wind farm. It was roughly about 50 megawatts from memory. And ultimately what we looked at was we had a chunk of data before the wind farm connected and a chunk of data post the wind farm connecting. And each chunk of data was, I think, roughly about a month, give or take. And so we had a look and we found the 95th percentile distortion values for each individual chunk, did that in isolation. And we looked ultimately at what the 95th percentile values were doing pre and post connection of the wind farm. Simple as that, nice and easy. Didn't kind of dwell down into transients and instantaneous impacts. Just looking at high level, what might we be able to expect when we connect? And what we can see is that we see a minor, and I say minor, 0.1% of the nominal voltage increase at the 5th harmonic. Everything else falls below 0.05% other than the 7th, in which it actually goes down. So why I say that it's minor is because if you're familiar with the Australian standard 61003.6, if you allocate a particular connection, if you do all of your calculations and your sums and everything, and you come up with an allocation of less than 0.1%, the standard says you should give them 0.1% because it is low. It's low risk. If they can meet a 0.1% increase in voltage, then you should be kind of pretty happy with that. So these values that we're looking at are fairly minor. And from memory, again, all of the information's in the report, but from memory, the connection point on the network was actually quite weak here as well. And so you'd be safe to assume, or safe to have assumed, that the impact was going to be much larger, but actually we found that ultimately, if you look at the THD, it actually goes down because of your 7th order there. Very interesting. So we did similar analysis for a bunch of solar farms of varying sizes, of varying connection locations, various topologies, even voltage levels, all sorts of things. And what we find is that solar farm 1 has ultimately the biggest, and the size of that solar farm from memory was actually the smallest. I think solar farm 1, 2, 3, 4 goes up in nominal ratings. And so we actually see that really, again, the impacts that we can expect, or the impacts that we actually measured, were either quite minimal or actually attenuating your ultimate voltage levels. Again, very high level, very simple and statistical, long-term probabilistic kind of impacts. But what we're not seeing is that substantial jump in distortion levels as soon as things connect. So moving on to Netherlands and looking at the sites, the suitable sites for which there was data that was available. Ultimately, what we had to do, I won't bore you with the process, but ultimately we had to download PDS, run a whole bunch of image processing to actually turn these images ultimately into values, and then was able to look at the trends over time. But if you're interested, there's the website there. You can go and have a look. All that data is still there. I had a look at it the other day just to make sure that it was still running. Absolutely is, still firing on all cylinders. And what we were able to do was actually get the THD values for each. So what you can kind of see, it's in that map. You've got little circles, and in those circles is a number. That's the number of substations that is in that area. You can zoom in and it kind of spreads out and you see where the substations actually exist. And so what we were able to do is pick the sites that we were interested in, and the sites that we were interested in are ones that had large offshore wind farms connected and operational with enough data prior to the connection of that wind farm so that we could see that impact, that trend. And what we see by and large is that generally we get this downward trend all the way to date of commissioning, and then we see it just kind of flatten out. You see pretty consistently that there are seasonal trends that occur across the years. So you kind of across 2014, 15, 16, so on. You can see these little peaks, and then kind of goes into the troughs in the middle of the year, and it kind of peaks again around winter for them, and then troughs again, and then you see this natural variation, which is to be assumed or to be expected. But you see this consistent downward trend, and this is the date of commissioning of the actual wind farm itself. And once we see that, we see again still those natural variations, but that trend is now flat. We look at other sites and we see a similar factor. Like I say, I think we ultimately had enough data for, I think, 4 sites, and 3 sites showed a very strong, or a statistically, what's the word? A statistically, can't remember the word here. But ultimately, we're seeing something that statistically we can describe as a decline in THD, and then after commissioning, we see that it kind of just flattens out and everything's fine. So why? We're getting more harmonic sources on the network, but everything that we're seeing is either things kind of being okay, not a huge jump, or actually things are getting better. There's a lot of reasons that this could be. One could be that part of it could be that the technology is getting better. Switching algorithms are getting smarter. They might be interacting with each other and causing sorts of phase cancellation, ultimately reducing the overall distortion. The management methodologies may actually be so strict that there's a lot more mitigation around syncing harmonic currents much more frequently, and ultimately reducing the overall distortion. But it gives us a good yardstick. It gives us something that we can kind of hang our hat on and say, well, okay, we're not in the woods yet. We obviously have some work to do, but we're not hitting these doomsday kind of levels of harmonic distortion. So that brings us to harmonic allocation. So as I mentioned, there's a number of different impacts that actually impacts the overall distortion. Part of that is the allocation or the management methodology that NSPs actually employ. Harmonic allocation is given a few different names depending on who you're talking to, but ultimately what we're talking about here is assigning a harmonic current or voltage emission limit to a connecting customer, and they are required, as per their connection agreement, to limit the amount of current that actually flows out of their installation. So there are many methodologies available, and we reviewed, I read so many grid codes and electricity rules and all sorts of things. And ultimately what I found is that we could actually break it down into 2 fairly basic categories. There are variations. There are all sorts of variations on each of the two big ones, I guess. But really, ultimately, what we can show is that we can chop it down into two categories. One being fixed allocation methodologies. And when I say fixed allocation methodologies, I'm referring to, as an example, IEEE 519 for anyone who's familiar with that document. I'll show you some of the details of that actual document in a second. But another one is network forecast methodologies. And so this is what's actually being done in Australia. And it's been given that phrase for a good reason. But ultimately, what I want to highlight here is that the methodology is susceptible to uncertainty. So jumping back to fixed allocation methodologies and considering the IEEE method, but also there are different methodologies, not the IEEE methodology that exist in France. The TSO there, RTE, have their own entirely own methodology, and even ways that they manage harmonics in general is completely different, which is I appreciate. And also FinGrid have their own, but really they're all kind of just different versions of the same thing. Really, it all boils down to simply a table or a very, very simple equation in which basically all you need to know is the short circuit ratio of the installation itself. So that is the nominal agreed power of an installation, whether that be a generator, a customer, or other, and the fault level of the network at the point of connection. And using this ratio in the IEEE 519 document, you then given just a suite of harmonic current emission limits across all different harmonic orders, and also a limit of total demand distortion. So that is, I won't go into it. If you're interested, you can do some reading. So fixed allocation methodologies are very restrictive, as you might be able to start to pick up. These tables are very simple to use, don't get me wrong, but what we have found is that for many Australian networks that we have looked at in this project and we have reviewed and discussed and thought about and modeled and all sorts of things, this method just doesn't work because it is based on a whole host of assumptions of the network that to which it is being applied. So the IEEE 519 is predominantly used in America, a little bit in Canada, and a handful of other countries. It's a bit like the metric system, really. There's a few people kind of holding the torch still, but it's limited in its application, and we can show that particularly with Australian networks, it just doesn't work because long feeders have a very, very high impact on what will ultimately result within your network. And what we found is that in Australian networks, quite often, if we use this sort of approach, we end up with cleaning levels being exceeded by a substantial amount. So it's very, very dangerous to use, in my opinion. But it's built for a purpose. Its purpose is not in Australia, in my opinion. So moving on to network forecast methodologies. And so this is what's used in Australia. There is a technical report published by the IEEE. I've referred to it already, 61000.3.6. And the reason that we've given it the label network forecast methodologies is because it's not strictly, it's not explicitly explained in the standard, but the assumption is that you have a very good idea of what the final state of your network is going to look like. So if we look at a very, very simple distribution system with a couple of long feeders on it, or maybe it's sub-transmission, and if what we can show is that if this is what you assume your network to be, once everything's connected, everyone's generating or everyone's emitting their harmonic emissions as you'd expect, then the methodology works out really quite well, and everything's quite good, and you reach your planning levels. No one's unduly penalised, but you have to make that exact guess. If you get that guess wrong, all of a sudden, either your distortion levels could be well above your planning levels, or you could be substantially penalising a lot of connections. When I say penalising, I mean requiring them to install harmonic mitigation filters, passive filters. That may sound nice and easy to do, and you know, the appropriate thing to do. But when we start talking about, you know, passive filters that are 10-20% of the nominal rating of the actual generator itself, which can no longer meet its reactive power capability because of the whole congregate capacitor that you've got connected there, all of a sudden it kind of seems to be a problem. And when this starts happening regularly, so we performed a bit of an unofficial survey during this project, and we found that roughly about 95 to 99% of generators were requiring harmonic filters. There was the odd one or two that didn't, and there was a lot of discussion as to around to why they don't need it. There was a lot of arguments, there were a lot of disputes. So we will try. So yeah, this is what we're trying to address really. So I mentioned 61306, which has been adopted by Australian standards as a standard, and therefore by law, but it has not reached that level of standard, international standard by the IEEE. So it has achieved the status of a technical report. By definition, by the IEEE, technical report is ultimately a bunch of good ideas, ultimately. Something that needs to be used with substantial or sufficient engineering judgment, and good understanding of the implications of the decisions that you're making. And the experiences and the discussions that we've had here in Australia kind of suggest that's not actually happening. So what happens, what I would like you to think about is when we start talking about uncertainty, okay, 20, 30, 40 years ago, it might be okay for a lowly distribution network service provider to have a look at their network and go, yep, 2 feeders, roughly, you know, they'll be evenly distributed, and you can run the process, you can do your calculations and go, yep, there's your allocation. Anyone who comes along, that's how you do it. Done. And that's suitable, and that was okay. And for a little while, it kind of worked. But what if this is the network that we get? And this is kind of the network that we're expecting now. What we can show is that instead of allocating what we had been allocating, it actually should have been significantly less than what we were allocating. And so now we're kind of in this field, in this area of uncertainty. And so I say uncertainty because, well, I've just mentioned, you know, if we knew that this was coming, then to all of the loads that had come earlier, we would have allocated a smaller amount, but we didn't. And so now it's very possible that we could be kind of operating this very high level where our planning levels are exceeded. Now that goes against exactly what I presented 10 minutes ago with distortion levels and what they're doing, and completely fair, but we're kind of at the start of this. We're heading towards this. And so you can start to imagine that things may be ramping up at any given point. And certainly there are certain factors and certain complexities that are a little bit hidden in this figure. Namely, I'm talking about remote resonances and the impacts of loads and passive components of customer installations, what they actually have on the impact they have on the harmonic impedance and ultimately the harmonic voltage. So it's important that we are robust in the way that we are allocating harmonic emissions. There was a paper, and there is going to be a second paper in ways to manage this. And it's all around kind of probability. It's all around implementing good planning practices, defining network limits, defining maximums, and kind of taking a probabilistic approach to, well, okay, we expect, or we know that there can be no more than, let's say, 50 megawatts of generation to exist within this network. Let's say that 25% is almost certain, and the remaining 25%, has a sliding scale. Those sorts of things, and they're really thought starters, I suppose. They're not fully developed ideas. They are really just ideas to try to apply not a quick fix, but I suppose a practical fix while still implementing the Australian standard methodology. That's blasted through harmonic allocation nice and quickly. We're going to jump straight into source aggregation. So when we talk about harmonic source aggregation, and I apologize for the speed, I'm just trying to get through. There's a lot to discuss here, so plenty of time for questions later. So when we talk about source aggregation, what we're talking about here is if we've got, let's say, two individual inverters, let's say an individual solar farm, you can assume that there may be two solar inverters that are connected quite close to each other. They are exposed to very, very similar conditions that are in the same site, for example. They're exposed to the same weather conditions. The generation source is being exposed to very similar conditions between the two inverters. So you'd be very reasonable to assume that the harmonic current emissions from each of those generators or each of those inverters is going to be roughly the same. And when I say roughly the same, I am also talking about phase angle as well, and also time of emission. And so if we look at the current that is actually flowing back into the system in this circuit, we've got harmonic current from the first inverter, we've got a harmonic current coming from the second inverter. We would assume that the current that flows into the system to be roughly the summation of those two currents. Arithmetic summation. And when I say arithmetic summation, that is ultimately assuming there is no phase angle difference between those currents whatsoever. Now, this is the process that is generally required by NSPs in Australia when undertaking pre-connection compliance assessment modelling. We assume that there is no diversity between harmonic sources within a network, within a site. So you might have, 40 individual wind turbine generators or 20 individual solar inverters, and the harmonic current from each one of those sources adds arithmetically as it kind of flows into the collector network and ultimately injects into the grid. So we looked at a plant for which we had quite a substantial amount of data. The graph that you can see on the right-hand side of the slide here is a single feeder of a multi-feeder generator. It's a large wind farm, which is, I think it was roughly 320, 350 megawatts. I can't quite remember. But we had multiple collectors, multiple feeders, and each one of the collectors had a number of individual wind turbines that were connected directly to it. So we had the meters connected at the terminals of every single one of the generators on one of the feeders. There was a total of 8 individual wind turbine generators. You also had the aggregate measurement of the collector feeder of that entire feeder. And so we were able to look at, well, if we aggregate all of these and compare it with this, how close do we get? It was over a 10-day period, so it was long-term. The measurements were 10-minute average values. Again, we're talking about statistical, long-term probabilistic values. And we also disregarded any measurements that fell below the measurement threshold, which follows another IEEE report. I can't remember exactly the name of it. Someone might be able to refer it. So really the hypothesis or the test here is that if there's no phase angle difference between each of the harmonic sources, then the current that we should get through this collector should simply be the summation of what we measure at the terminals of every single one of the generators. That's simple. Now, first we tested our system, not just the measurement system, but also the analysis, the process in which we read in all of the data, which we performed all of our calculations and everything. So what you can see here is actually the fundamental current. To get that kind of correlation for a harmonic source would be fantastic. That would be great. I'd love to do that, but you'll see in a second. So this ultimately confirms that our process is good. We can see that fundamental current kind of follows exactly what we expect. It also is quite interesting that, so what we've got here is the measured current through the collector feeder and also the calculated current. So this is simply the summation of all of the individual generators on the y-axis. And so if this is, and when I say this, if this is a good assumption, if there is no phase angle between individual harmonic sources, we should get roughly a straight line that we can draw through most of the scatter points with roughly a gradient of 1. So it follows kind of, you know, at 100 amps for the measured calculated collector current, we should see a calculated current of roughly 100 amps, 200, 300, so on, so on, so on. And we should kind of see roughly a y-intercept of 0. And as you can see, we've also got time series kind of analysis that we've got there. So that's ultimately our hypothesis, our test. If we hit that, then things are looking good. Second. What we see instead is a substantial amount of diversity. Now we did this for every single harmonic order between the 2nd and the 50th, 49 total scatter graphs, I'd say. Now, important to note that I mentioned earlier that we disregarded any of the measurements that fell below the measurement threshold. That's important because it ultimately disregarded a significant amount of the harmonic orders. So we were actually left with the 2nd, the 3rd, the 5th, the 7th, and the 13th. They were the only harmonic orders that had enough measurements to actually perform analysis on. Everything else fell below the measurement threshold, which ultimately suggests that, you know, there is a significant amount of diversity between those sources. The emissions themselves are low, and it's resulting in really just nothing happening. So to decipher this graph a little bit, the orange points identify situations in which the calculated current, the summation from each of the generators, suggests that the emissions through the collector should be above the measurement threshold. But actually, when we plot it on the measured current, or we look at where it's actually the measured current through the collector, it actually falls below the measurement current threshold. And this is where actually the majority of measurements fall for most harmonic orders, including those with enough data to actually analyze. So really the only ones in which we've got not a substantial amount of diversity are these ones in the blue. You can see the black line here is ultimately that line that suggests that there is no diversity. So if the data points are following that line, then we can say that, you know, there's rough alignment of the individual sources. But what we see, and this is for the 11th harmonic order, that significantly it overestimates. It substantially overestimates and consistently overestimates. Now there are certain areas where the emissions actually exceed what is being emitted by the individual generators. We're not exactly sure where that excess current has come from. We just don't have the level of detail in the data to actually provide enough analysis for that. More in the report if you're interested. And so then we started to look at, well, how big of an error did it actually create? And you can see that it varies for harmonic orders, and generally speaking, other than the seventh, it kind of starts to, the range increases as the harmonic frequency increases, and kind of tops out at about 100, 800, 900% or so. So there are serious impacts, and this is really important when we start looking at harmonic modeling, because if we're overestimating, then you'll almost guarantee that you're going to need a filter. Again, filters are expensive. They have impacts on how the network operates and all sorts of things. So we want to try to avoid that as much as we can, which flows neatly into the next section of harmonic mitigation. So harmonic mitigation, very briefly, in Australia, and you may be aware, but at the moment, harmonic mitigation ultimately is a matter of requiring customers to connect harmonic mitigation right at the point of connection of their site. And what that does ultimately just sinks, or it provides a low impedance path for the harmonic current to flow straight out of the generator into that filter and stops it from emitting into the network. That's it. And poking into the Australian standard of 61003.6 a little bit further, what you'll find is that what the standard is trying to do is actually manage your harmonic distortion levels at a single point in the network. And so again, if we've got a very simple radial distribution network, it might be, and this is all to do with harmonic resonances due to line charging capacitance, interacting with your series reactance, and what you can actually find is that the largest harmonic impedance in your network may not always be at the end of a feeder. It may actually occur, well, it could occur anywhere. And that's all due to your RLC components interacting with each other and capable of causing a parallel resonance, which ultimately amplifies your harmonic voltages. And so the Australian standard is trying to manage the harmonic voltage at a particular point in the network. And the way that this has been implemented is by connecting filters at the point of connection of every single generator, so that the currents don't flow into the network to the point reaching, and the network reaching planning levels at this point or exceeding. Now, I won't go into any more detail. We'll see it in the examples. So I've done two very, very quick examples. I've done a lot more work on this, and very, very happy and very willing to talk to anyone who's interested in this, because it's a very important finding of this project, I think, and one that I think needs to be socialized as much as possible. So I won't go into the detail just because I'm looking at time and running very, very short. So so I won't go into detail, but ultimately what I want to highlight here is that instead of requiring all of these filters to be connected at the PCC, we compared that approach after allocating your harmonic current emissions to everyone and making sure that everyone's meeting their emission limits and blah, 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 blah. Compared that approach to, instead of having all those filters connected everywhere, instead just having a single filter at the point where your harmonic impedance is actually at its highest, and compared the size of the filters that are required. We looked at a single harmonic order just to keep it nice and simple. And the filter design was actually really quite limited. So it was really just kind of trying to look at how the two methods stack up against each other, I guess. And this is ultimately where we sit. And so the harmonic order that was managed here was the 12th, because it was the lowest harmonic order that actually exceeded with the all of the details that were fed into the model. And so we looked at business as usual, and if we sum all of the filters that were required by the generators to manage that one single harmonic order at the 12th, we require a total of 760 kVAR, which doesn't sound like a lot, particularly for a number of large generators. But keep in mind that the filters are ideally designed. They're not C-type, they're single tuned. And we're also dealing with resonances here as well. And so really what the biggest finding here is the ratio between the proposed methodology, where we go and we connect the filter directly to the point of concern, compared to business as usual. And we come up with a filter that's 2.5% the size of the aggregation of all of the filters in business as usual. And also, importantly, what we find is that with the proposed methodology, not only is the filter smaller, but the overall impact that the filters have on the remaining harmonic sources and the impedance is significantly reduced. So what you can see here is that with business as usual at the 15th, it's a little bit difficult to see, but with business as usual, we're mitigating the 12th order, but it ultimately results in the 15th order actually exceeding planning levels, because these, whenever you connect a harmonic filter, you're shifting harmonic frequencies or harmonic resonances, sorry. And so there's a lack of communication almost in the design process, and you can ultimately impact the capability of not just the network to meet compliance, but also other generators or other customers that are emitting harmonic emissions. They design their filter for a particular network scenario. You come along, strap on your filter, and then all of a sudden the scenario is completely different. The harmonic impedance is entirely different, and you end up with planning levels being exceeded. So the proposed methodology, the impact that it actually has on the rest of the network is minimal. It's focused. It's only dealing with what you want it to deal with. So again, I won't go into much more detail because I think we've kind of covered off most of it here. This kind of highlights the ratio of the filtering that's required. Very interesting how that actually came about, but again, everything's in the report. We ran the same with a much more complex network, and this is a real network. It's also it's anticipated to ultimately connect to a renewable energy zone. So we can expect a lot of renewable energy to be connecting throughout this network. The colors you see there are different zones that we split it up into. And ultimately it was a matter of connecting just as much generation as we could, or harmonic sources really is what we're talking about, connecting as many harmonic sources as we possibly could across the network and looking at how we actually mitigate the harmonic emissions. Again, taking that business as usual approach compared to, actually just managing the harmonic impedance where there are actual issues. These colors you can see, the network was also divided into strong, normal, and weak areas, and that ultimately decided the amount of generation that was actually capable of being connected there without introducing further issues like voltage regulation problems, reactive power, and all those sorts of things. So importantly, really the first stage, we connect, I think, about 500 MVA throughout the network, and then all those green spots are where the harmonic sources are actually connected. And what we found, most interestingly, is that the harmonic emissions were actually largest 200 kilometers away from the nearest harmonic source. That's what I'm talking about with these harmonic resonances and those sorts of issues. You can actually result in reaching your planning levels or exceeding your planning levels a long, long way away from where the actual source of the harmonic current is. And so ultimately what we found was that this was able to be managed really quite simply, because this is quite a weak part of the network. We're able to manage it just by detuning the upstream capacitors. Fairly simple, fairly limited process. We then stepped through stage 2, stage 3. I think there were about 8 stages in total. And we just kept kind of well, it was almost like whack-a-mole. A problem pop up, you connect a filter to the point where there was an issue, and the size of the filter is minuscule, and you just continue on. And the amount of fundamental power that was being injected into the rest of the network was just phenomenal. Not anything that it would ever be able to hope to accommodate without significantly upgrading transmission lines and connections and all sorts of things. But we're able just to manage harmonic levels just by chucking in little filters all over the place, which is really interesting outcome. And like I say, something that we're really trying to socialize. And again, this is simply an idea. It's a long leap from an idea to practical application. But that's why we want to have those conversations, is because we want to see it in practical application, because we believe it is the best way to go. So some of the insights, some of the analysis here, what we're talking about is significant deviation from present day practices. Let's get that straight. And we need to do a lot more work to implement it confidently and competently. But yeah, certainly, yeah, here to have that conversation, anyone who's interested. There's a lot of experiences ultimately that we need to generate, and there needs to be a lot of thought and discussion as to a lot of the minute details, specifically like how do we actually apportion costs and responsibility of things like network-led solutions of harmonic mitigation, all sorts of questions that I'm sure are probably running through your head right now. So into the final section, preliminary evaluation of compliance assessment. So this topic is huge. It's actually the topic of a future grant that is currently in process. We are hoping to get this work moving. If this is something that you're very interested in and could even throw some resources at, please do get in touch, because it would certainly benefit from industry buy-in. So all of the issues that we've been talking about and all of the details that we've kind of been hinting on, and the impacts and the outcomes and increased voltage level, harmonic voltage levels, and all those sorts of things, it all comes down to compliance assessment, because really there's 2 points at which compliance are assessed: pre-connection, post-connection. Done. Now, why do we need to look at this? Well, because we know, and I say know very confidently, we know that the processes that we are using to develop harmonic models and ultimately assess pre-connection compliance is incorrect. It just does not work. It is, generally speaking, we find most often that it overestimates by a substantial amount the expected harmonic emissions at the point of connection. Again, significantly increasing the likelihood of filtering being required. And so there is a substantial work package all in that that needs to be undertaken so that we can do that process better. And then post-connection compliance assessment. Now, why that's important is ultimately it's how do we determine whether or not a plant is compliant. There's a host of issues. I think majority of them are, yeah, I think we'll be, yeah, I think they're all sitting there. So just very briefly, when we talk about pre-connection compliance assessment, we're talking about harmonic modeling, harmonic representation of inverter-based resources, of collector systems, of transformers, of reactive components, of the network itself. Now, what is being used? Well, all of what I have seen, and we do a lot of this work, particularly over here on the east, is all of the models that are used are all 50 hertz models. Now, for a number of components, that is absolutely suitable. We apply the frequency dependent component. We know how to model it in the harmonic domain. Everything's fine. But what we're seeing is a lack of prescriptive methodology in the representation of inverter-based resources. Harmonic modeling of inverter-based resources is where there are a lot of inaccuracies that are being injected into the process and ultimately resulting in those overestimations. But also the representation of the network itself. So what we're seeing is a lack of engagement, generally speaking, not all the time, but generally speaking, from network service providers. And ultimately what's been implemented is what's colloquially termed as the impedance polygon method. So what you can see on the right-hand side is a whole slew of red dots. Now, each one of those red dots is a harmonic resistance and reactance. So resistance on the x-plane, on the x-axis, reactance on the y-axis. So in there, I think is about 13,000 points. And so each one of those points actually represents a network operating scenario. And what we find is that rather than sit and think about a suitable representation of the network or a handful of scenarios that are absolutely necessary to consider when looking at the operation of the network or the harmonic representation of the network, we just get told, do all of them. And so that is do 13,000 of them, which boggles the mind a little bit. But what it means is that instead of being kind of a small polygon, we see this huge kind of representation of the network. And the bigger and bigger that polygon gets, more and more likely you're going to require a harmonic filter. It's as simple as that. And so now I guess it's important to note that the impedance polygons are not mentioned once in the Australian standard. It is something that is simply rose out of experience and different studies that have been run elsewhere for different purposes as well. And ultimately, it's kind of been unofficially decided that this is the way that we represent the network for harmonic modelers. And what we're finding is that it's just not realistic, and it's significantly increasing the amount of filters that are required, and yeah, ultimately something that we're trying to avoid. So there's a lot to tease out here, but ultimately what we're trying to do, or what we would like to do, is to provide that prescriptive methodology in pre-connection compliance assessment across kind of the whole gamut of what's required. Similarly with post-connection assessment, so there are a whole bunch of ambiguities in the existing Australian standard. The definition of compliance itself is ambiguous at best, and so actually being able to prove compliance becomes very, very difficult. Also, there are difficulties with the state of the network that actually impacts the capability of a generator to actually meet its compliance. It ultimately shows that if the network is not in the state that you expect it to be when you allocate and perform pre-connection compliance assessment, the generator is very unlikely to actually meet compliance. So whose fault is that? Is it a problem? If voltage levels aren't out of control, then no, it's not a problem. But ultimately, it all comes down to definition of customer contribution, how it's assessed, where it's assessed, when it's assessed. Yeah, it's a very, very big topic, that, and it's difficult to kind of go into without spending another 4 hours on it. And another thing that we've really highlighted as an important part is the appropriateness of planning levels, compatibility levels. So if you've ever mapped out the harmonic planning levels in the Australian standard, this is ultimately what they suggest, and that is we kind of expect a maximum at the fifth order, and it kind of decreases keeping on your characteristic harmonic orders, which ultimately follow the 3K plus minus 1 So your 5, 7, 11, 13, 17, 19 are your high priorities, and generally where you'll see the most amount of distortion, and everything else should keep kind of quite low. Now, is this the best way to go? Is it important that we keep the 15th to 0.38? You know, is 0.41 okay? Who knows? It's all those little questions that really aren't in the overall management methodology. Those things aren't really kind of made very clear. So we're hoping to provide a bit more prescriptive methodology and provide something a little bit more practical and applicable. So just 10 minutes over time, but just wrapping up. High level, distortion levels are not increasing linearly. Allocation processes are shown to be difficult to apply and very sensitive to renewable energy generation. Measurements show that aggregation of individual harmonic sources includes substantial diversity across all harmonic orders. Revised process harmonic mitigation shows promise and limiting impact on customers and reduce overall costs, not just for customers, but also NSPs as well. And existing compliance assessment requirements and methodologies are ambiguous and capable of leading to dispute. And there is a lot more work that needs to be done in this area, but that is where we are at for the moment. So, probably sick of hearing me talk, so I'm happy to open it up to questions. Also, like I say, please do feel free to copy down my details there and reach out at any given point.
Thank you very much, Jason. Thank you for the great presentation. I found it very informative and learned a lot. So as Jason said, it's time for questions. If anyone has got any question, please shout out. No question from audience. Maybe I can ask one question. Jason, from your opinion, as you know, the power systems all around the world are undergoing a major transformation, basically decarbonization. Every jurisdiction has got this ambition of net zero and running the power system 100% renewable. Do you think from your experience it is possible, not saying 100% renewable because that covers hydro as well, let's say 100% inverter-based resources? I wanted to know your opinion, whether it's possible to do it, given that inverters, uh, they can cancel or absorb harmonics, but they are the sources of harmonics in the power system.
Yeah, look, I mean, it's a multifaceted question. 100% inverter-based resources. I mean, look, well, I guess the way you open it is, yes, everything's possible. Whether it's economically practical, maybe not. In terms of harmonic sources and harmonic interactions, look, it's a really interesting one. There's more and more conversation now around, well, just conversation. There is a lot more happening now with grid forming inverters. And this is a question that I raise every time I see a presentation or hear a discussion around grid forming inverters. How do they operate in terms of harmonics? Because ultimately it's still an inverter. It's still a harmonic source. It's a switching component. It's non-linear. And look, unfortunately, I'm yet to hit the right person at the right time to get an answer that I'm comfortable with. Because quite often it might be, someone that's very well adept in, power electronic controls or you know, dynamic stability of inverters, and, you know, all sorts of, you know, there's such a wide gamut. To hit the right person that knows how they operate in the harmonic domain, you know, it takes a little bit of searching. So I don't know yet, is the short answer. I think not just for harmonics, but for other things as well, we're going to be reliant on synchronous machines of some sort, whether that be coal-fired generation, synchronous condensers, some spinning mass that ultimately gives us the capability to absorb a lot of harmonic current emissions.
Yep.
So until we're at that point where we're running really, really lean with some synchronous machines, I think everything's kind of, you know, it's manageable, I guess, is the headline.
Yeah, agree. Even I think there should be a coordination between maybe switching frequencies as well, having different switching frequencies, because the highest harmonic distortion is exactly for inverters at the switching frequency.
Absolutely,
Yeah.
absolutely. And yeah, and like that, there's a lot of very clever things that these inverter manufacturers can do. You know, we've been in discussion with multiple OEMs around, you know, what they do with their harmonic emissions, how they manage it. There's been particular projects where there's been a concern around a particular harmonic order because it might align with the resonance or something. And they say, yeah, no worries. So they go in and they reprogram the inverters, and it's called sympathetic switching, I think. And they ultimately purposely create a phase angle at a particular harmonic order, and you see this significant dip in the distortion. Now, you kind of say, well, why don't you just do that all the time? It's limited in what it can actually achieve, and ultimately the inverter has to prioritize other things than just harmonic emissions. But in saying that, yes, there is a lot of clever things that can happen, and there's a lot of coordination that could be possible. And those sorts of little tuning ideas and things, I think will start to gain a lot more traction fairly soon, because ultimately it's the appetite to be connecting harmonic filters is waning, I think, particularly with the people that we've been talking to. Yeah, it's I think people are starting to realize that it's a bit out of control.
Yeah. Yeah.
Not optimal, not resulting in a good outcome.
Yeah, exactly. No, I agree. At the end of the day, I think harmonics are kind of reactive power, so they need to use the capability of the inverter depending on the priority,
Yeah.
and conditions. It's definitely different.
Yeah, absolutely.
Cool.
Yeah.
Any other questions from the audience?
Ali, I can go.
Yes,
I
please.
have a question. Thank you, Jason, for a nice presentation. I've just got a question. Which tool did you use to model the network? And what was your approach to locate the filters? As you said that you find a best location to put the filters. And did you use any optimization for your approach or no? Thank you.
Yeah. So the package that we used was PR Factory, I think was question number one. And so that's as we've been saying, it's, you know, it's RMS, it's steady state, it's long-term kind of stuff. We're not looking at transients or anything like that that would require something like PSCAD. And so the representation of the inverters themselves were gained from manufacturer data. And don't worry, I understand that I've just told you that what they do is really inaccurate, but it's the information that we've got at the moment. We also just need to feed in an impedance representation, really, of the generator is the most important part for these sorts of things. And in terms of optimization, look, the way that it was done, well, The way that we really kind of honed in on this finding, this outcome, was kind of with this equation. But what I can show you and what you can see in the report is that if you find the point on the network at which the impedance of the harmonic order that you are interested in, let's say it's the fifth order harmonic, you find the point in the network at which the impedance is the highest, connect the filter there, that will be your optimal point, guaranteed, hands down. It's mathematical, and the connecting the filter at that point will result in the smallest rated filter that is required. But then, of course, there's practical implications like costing the filter, locating it in a particular, may not be financially viable or may not be physically possible to connect it at the particular point of the network. Let's say it's at this point, but there's plenty of space up here. You'll still get quite good efficiency connecting it away from the point at which the impedance is the highest, but the point at which the impedance is the highest is always the optimal position.
Thank you. And would that, let's say, filter would be enough for the whole network?
Yeah. So, well, what we can show is that if we connect a filter at the point at which the impedance is the highest, ultimately what you've done is you've unlocked a bit of headroom, so that you can actually have a higher amount of emissions. And what you'll find is that your planning levels, well, depending on your filter and depending on your network, but you may find that your planning levels will be reached with an increased amount of harmonic sources present on the network. It may also actually result somewhere else now, because this is no longer the highest impedance point on the network, so it may be occurring here or here, somewhere else. So it's really a matter of, like I say, I kind of mentioned, it's almost like whack-a-mole. You knock it down where it's a problem, and you can kind of keep knocking it down until everyone's happy, everyone's connected, and there's no issues with harmonic distortion. So it's really a matter of what is the end game, and if the end game is to get all of these 3, 5, 7 generators connected, then it would just be a matter of getting those connected, having the filters required, and then moving on. That would be it. But I mean, realistically, that's not that simple. But
Great, thank you. Last question, if I can.
Yeah, please.
So I would have you considered any sizing for the filter?
Sizing in what terms?
You know that each filter has a size limit, so we can have a very, very big filter. It does the job, but we don't have it in practice.
So are we talking about a physical size or a rating, like a
Rating.
Yeah. So yeah, absolutely. The as kind of shown here, it's difficult to kind of see, but as I mentioned, we looked at the 12th order for this one, and as you can see, kind of see. It comes in good. With these at the 12th order, we're exceeding by, I don't know what that is, maybe about 0.1% or something like that. With all of the filters that were connected, we can see that the distortion actually bottoms out. That's the business as usual. That's all your generators with the filters connected at their point of connection. With our proposed methodology, in which we connect to the point at which the impedance is the highest, we bottom out at 20 kVAR, which is 2.5% of the original filter size, and we're still well below planning levels. So yes, absolutely, we try to optimize, but also when it's in terms of resonance and when it's in terms of being able to connect it kind of wherever you want, the size of the filter is minuscule. It's tiny, and so it would ultimately be a filter of a couple of kVAR. But again, taking this idea into kind of practical application and reality, those sorts of things would need to be better thought about and actually designed, I suppose, in a practical sense.
Great, thank you, Jason.
Thank you.
Great. So we've got 5 minutes. It seems that there are no other questions. I would like to thank you on behalf of PES chapter, Jason, for making the time to prepare this presentation, and appreciate your time, and thank you very much.
Thank you all, and thank you all very much for having me and for the questions. And like I say, please do not hesitate to reach out. We've got plenty of reports. We do a lot of this work, and we're always interested to talk about power quality and all those sorts of things. So hopefully it's not the last time I speak to you all. Thank you.
Same here.
Thank you,
Have a
Jason.
good night.
Cheers.
Thanks.
Thank you very much.
Bye.
Thank you all.
Thank you, Jason.
Thank you, Jason.